You guys do it already? Problem on the board? Did you work on it? Welcome to class. Hope you all had a nice, fun Halloween, and now it's Christmas apparently. Because who cares about Thanksgiving? Let's go ahead and talk about this problem. So I just wanted to remind you of this because I feel like we kind of gave it short shrift earlier. When you're finding the equation of the equation of the plane given a normal vector, it's really kind of a very easy process if you want to do it the fast way. We know that the coefficients of x, y, and z should be the components of your normal vector. So kind of the fast way of doing this is just to say, well, it's negative 2 times x plus 5 times y plus 3 times z equals some constant. And then you can just plug in your point to solve for the constant. So I plug in the point 3, negative 4, comma 1, bless you, I'm going to get negative 2 times 3 plus 5 times negative 4 plus 3 times 1 equal to d. Let's see, that's negative 6 minus 20 plus 3. That's negative 23, I think. So then the equation becomes negative 2x plus 5y plus 3z equal to negative 23, or plus 23 equals 0, whichever way you prefer to write it. Kind of doesn't really matter. As a reminder, the reason why that works is because what you're really saying is, oh, do you have a question? For the equation of a plane? I feel like there's only I feel like there's only one equation of this plane. Like I guess I'm not I would say there's two different ways of finding it. Yeah, yeah. I was gonna mention that. So the other way is the more generic process where it's like, oh well, any point in this plane, the vector you draw from the point we know to the point we have, let's call that vector V. And no matter what point we've chosen that's in the plane, the vector V, which is just x minus 3, y minus 4, and z minus 1, that vector and the normal vector have to be orthogonal to each other. So we know that n dotted with v has to equal 0. So then we're going to say, okay, well, that's going to be my vector n, which is negative 2, comma 5, comma 3, dotted with x minus 3, y plus 4, z minus 1, and that has to equal 0. So our equation becomes 0 equals negative 2 times x minus 3 plus 5 times y plus 4 plus 3 times z minus 1. When we multiply it all out, we get 0 equal to negative 2x plus 6 plus 5y plus 20 plus 3z minus 3. And rewriting it, we get 0 equal to negative 2x plus 5y plus 3z plus 23. Or you can bring the 23 over and get the same equation. So the long way kind of shows better why it actually works the way it works. But then seeing that, you can always say, well, great, we know the coefficients are just the components of the normal vector. And it'll always work that way. It's kind of cool.
How did you get 23 in the first one? Because I know how to get it, but how did you get it?
So in the first one, what I did was I just said, we know the coefficients are going to be -2 for x, 5 for y, 3 for z. So we know that the equation of our plane has to be -2 times x plus 5 times y plus 3 times z equal to some constant. And the way we figured out what the constant was by plugging in the one point that we know is on the plane. Right? We know that the point 3, -4, 1 is on the plane. So we just plugged in 3 for x, -4 for y, and 1 for z, and then got -2 times 3 plus 5 times -4 plus 3 times 1 equals the constant, which is -23. Cool. Let's talk about more interesting things in space. So we have a couple distance from things to things formula. And I will be perfectly honest, I never remember these formulas. Like there's ones that do not stick in my head for whatever reason. So whenever I do these, I have to draw the picture. Now, I think I have thought of a way of remembering it that might make it easy to remember, or you might just be better at memorizing things, which is great. So we want to find the distance from a point to a line. And we'll do this via example, but then we'll kind of write out a generic formula here. So here's our problem. We want to find the distance from the point, and we're going to label the point as S. We're going to call it, it's going to be the point 1, 2, 3, to the line L given by the parametric equations x equal to 2 plus t, y equal to 2 minus 3t, and z equal to 5t. So here's our very generic situation. We have this line L, and we have this point that's presumably not on the line, although you could check to make sure, right? There's no way that that point's on the line, because if, let's see, to get the right x coordinate, t would have to be -1, 2 minus 1 is 1, but then 2 plus 6 is not 2. So the point's not on the line. Yeah. I don't think so. I just know, well, one, I'm trying to show you how it works. And two, I have to do it because I can't remember the formula. But that doesn't mean you have to do it that way. I think if you can remember the formula for the distance between a line and a point, that is perfectly fine. And I think I have a way of kind of making it easier to remember. I have a device that is like, I actually think I know it now, but not confidently enough to just write it out. So let's see. So we have this other point S not on our line over here. So let's say S is over here. S is the point 1, 2, 3. And we are trying to find this distance here. That is what we would like to find. But the problem is we don't know what that point on the line is. We don't know what the point closest to the point that's on the line is. But we can find some other point on the line. So for example, the easiest choice here is probably to let t equal 0 and say the point x is 2, y is 2, and z is 0 is also a point on our line. So let's say we'll call that point P, and it'll be 2, 2, 0. And that's by letting t equal 0. You don't have to pick that point, though. Literally, all of us could pick a different point on the line by letting t equal 0 or 1 or something terrible like a fraction, and still come up with the same distance, because it should always be the same. So what we're going to do is we're going to draw the vector from P to S. And we're going to draw this angle. So let's actually write that. So let's call this vector here is PS. And in this problem, the vector PS is, well, it's the S coordinates minus the P coordinates, bless you. So it's going to be 1 minus 2, 2 minus 2, and 3 minus 0. And then we also want the vector V that points in the direction of the line. Fortunately, that's really easy to find. It's just the coefficients of t in your parametric equations. So the vector v, the direction the line points, is 1 comma negative 3 comma 5. But yeah, I was thinking about this as I was walking over here and thinking about how we probably could do this by finding the projection of this vector onto this line and then finding the orthogonal complement. That's not what we're going to do, even though it would probably work because it's not the formula that's in the book and it's not what you should try to memorize because it's kind of funky. So all of these formulas really come down to trigonometry. So if I want to find the length of this side and I've got this angle and I can find the length of that side there, I should probably use the sine function because sine of my angle is equal to the opposite side length, which is d, which I'm trying to find, divided by the magnitude of this vector here, ps. I know I've said this before, I'm going to say it again. A question? Mm-hmm. Say it one more time. For the line p, so you mean for the vector ps? All I'm doing, so to find the vector ps, I'm taking the s coordinates and subtracting the p coordinates. Right? Whenever you have a vector that starts at the point and ends at another point, we're just finding the difference in the point essentially for the x, y, and z parts of it. So here's what I know. I know that when I see sine of theta, I want to make the cross product show up. That's what I'm really thinking about here is, okay, I know the formula using the cross product that has sine in it. So we're going to multiply both sides by the appropriate things. So here's what we're going to get. We're going to get that we multiply both sides by the magnitude of PS and the magnitude of V. So we have the magnitude of PS times the magnitude of V times sine of theta is equal to D over the magnitude of PS times the magnitude of PS times the magnitude of V. The magnitudes of PS cancel on the right-hand side. But I guess the better thing to say is, why did we even do this? Well, because this left-hand side here, this is exactly the magnitude of the cross product of the vectors V and PS. Right? That's the formula for, I should say, that's not the formula for the cross product because we're missing the direction of the normal vector, but we don't need that to find the length. So here, this left part here, this is just exactly the magnitude of the cross product of PS crossed with V. And it's equal to the length we're trying to find multiplied by the magnitude of V. So then I can divide both sides by the magnitude of V, and there's my formula. The distance between the line containing the vector V and the point S is going to be the magnitude of PS crossed with V divided by the magnitude of the vector V. Maybe you can memorize it. I obviously can't. But it's not like a failing, right? It's just like I don't remember that one. Once we talk about both formulas, we'll come back and kind of try to think of a way we might remember these. Let's actually do this problem though, because we haven't, right? We found the formula for the distance between a point and a line, but we still need to actually answer the question. I should point out, right, just as a few things here. S is any point, sorry, is not any point. S is the point not on the line. And P is any point you find on the line. We could all use different points. And then V is the vector in the direction of the line. So, in this particular problem, well, we have the vectors being right there. Our distance is going to equal the magnitude of, okay, PS cross V is going to be kind of gross. It's going to be negative 1, 0, 3. I shouldn't even be writing this here, really. Crossed with 1, negative 3, comma 5, divided by the magnitude of V, which is the magnitude of the vector 1, comma negative 3, comma 5. The bottom part's not too terrible. It's just the square root of 1 squared plus negative 3 squared plus 5 squared. But the top part, that's where we have to actually like do the cross product part. So to find our PS crossed with V, it's going to be the determinant of this fun thing. PS first, negative 1, 0, 3. V second, 1, negative 3, 5. And we do the usual dance. We have I times the determinant of 0, 3, negative 3, 5. Minus J times the determinant of negative 1, 3, 1, 5. Plus K times the determinant of negative 1, 0, 1, negative 3. So simplifying this, we get, let's see, 0 minus minus 9 is 9I. Negative 5 minus 3 is negative 8. So we have minus negative 8J. And 3 minus 0 is 3K. So there's our, whoops, that looks very slanty there. So that, or we can write it like this if we prefer, right? Either way, 9, 8. Oof, okay. So then the magnitude of that vector is going to be the square root of 9 squared plus 8 squared plus 3 squared. Not very nice numbers, but a totally fine process. We could simplify that if we really wanted to. Our distance is going to equal the square root of, let's see, 81 plus 64 plus 9 is 90, is 154. And 1 plus 9 plus 5 is, sorry, 1 plus 9 plus 25 is 35. So there's our gross distance. Okay. And that's kind of, I mean, there's not a lot else to say about it. Your only job really, so when you're faced with a problem like this, your job is to pick a point on the line and then make sure you identify both the vector from the point to the point that's on the line and the vector that's in the direction of the line. And in my opinion, well, I should say that formula is the easier one, I think, to remember. It's the harder one to actually calculate because you have to do the cross product, which is just less easy to do than the dot product. Okay, we're going to come back to this, but let's look at the other kind of distance between things formula that we usually talk about. Okay. Yeah, of course. Yeah. Remind you, I do post the lecture notes on Canvas. They're very accessible. It might look nicer than the picture you're taking, but interesting. Okay, so distance from a point to a plane, which you might think has like the same kind of formula, and it's not. Although it's similarly derived. I always screw it up, but I'm not going to screw it up this time. But I usually screw it up when I try it first time. So let's look at the following example. Let's say we want to find the distance from the point S, which is 2, 1, 6. And in this textbook, S is always the point that's not on the thing. And then P is always the point that we pick to be on the thing we're looking at. So from that point to the plane, 4x plus 6y plus 3z equal to 12. And a quick check, yep, S is definitely not on the plane because you're getting 8 plus 6 plus 18 when you plug in that point to that plane. So it's always worth checking because the distance could be 0, and you feel really silly to do all this work to get 0 when you could have just plugged it in and checked. It's probably never going to happen. But you never know. Some teachers like to ask tricky questions on exams. So here's our plane. And let's say our point is over here. So here's the point S. And here's the mistake I always make that I'm not going to make this time. We don't drop a perpendicular from S onto the plane. We pick a point on the plane. And again, you can just pick any old point that satisfies this equation. You could pick 0, 0, 4 or 2, 0, or 3, 0, 0 or 0, right? There's lots of choices here. Pick some point on the plane. I'm going to pick a different point than is in the notes here. I'm going to pick the point 3, 0, 0. And that's my point P. And then what we want to do is you want to draw two things. You again want to find the vector PS. So we're really interested in what's going on here. And then we want to draw the normal vector perpendicular to the plane emanating from the point that we have labeled on the plane. So we want this normal vector here. We want to draw it kind of tall. It doesn't really matter if we're drawing it the right length or not. It just has to point in the right direction. Good news. Good question. So, one more time. I specifically, you could draw it anywhere, but we want to draw it emanating from the point that we have labeled on the plane so that we can draw a triangle. Good news, we know what the normal vector is, right? It's just the coefficients of x, y, and z in the plane equation. So our normal vector is the vector 4, 6, 3. And now, this is always the part that used to throw me off. We're trying to find this distance here. Right? It's the same as this distance over here. I just didn't draw it over there. So, much like before, we're going to look at the angle theta and talk about which trig function we need to use to find the length d. And in this case, it's not going to be sine, it's going to be cosine, because cosine of theta is the adjacent side divided by the hypotenuse side. So here we're going to say that cosine of theta is equal to the length we're trying to find divided by the magnitude of PS. And then just like last time, we're going to multiply both sides by things to make the formula that we think should show up. In this case, we're not looking to make the cross product formula show up. We're looking to make the dot product formula show up because we see there's a cosine. So we know on this side, well, we know that the vector n points that way, the vector ps points that way. So we want ps dotted with n over on this side. And so we're going to multiply both sides by the magnitude of ps and the magnitude of n. And then the magnitude of PS cancel out on this side. This left-hand side is just the dot product of PS and N. But there's a problem. That dot product could be negative. And this length should be positive. So we need to take the absolute value of the dot product over on that side. Otherwise, we might end up getting a negative value for a length when we want to find a positive value. It seems kind of weird, but it can happen. So here, we're going to get the absolute value of the dot product of PS and N, and then we're going to divide by the magnitude of N. And that is going to be the distance we're trying to find. Much easier to calculate. So in this case, let's see. Our vector PS is the vector that starts at the point 3, 0, 0 and ends at the point 2, 1, 6. So its coordinates are, or I should say its components are 2 minus 3, 1 minus 0, and 6 minus 0. And then our vector n, we've already written it down. It's the vector 4, 6, 3. So then our distance here should end up equaling the dot product of these two vectors. So that's going to be negative 1 times 4 plus 1 times 6 plus 6 times 3. And even though we don't need it, I'm going to put the absolute values around there anyway, divided by the magnitude of the vector n, which is the square root of 4 squared plus 6 squared plus 3 squared. Simplifying this, we get, let's see, negative 4 plus 6 plus 18 is going to be 20, divided by the square root of 9 plus 16 plus 36 is 61. And I would probably not bother rationalizing that denominator. Okay, so here's what I think I've come up with that might make it easier to remember which formula is which. They're basically the same formulas, kind of. Right? They're both the PS vector, either dotted or crossed with the other vector you get to find, divided by the magnitude of the other vector you had to find. either the normal vector for the plane or the direction vector of the line for the line. And here's how I remember which one's which. Line rhymes with sine. And the line formula, we had to use the cross product because there was a sign in there. It's the best I've got. So if you're trying to find the distance between a point and a line, it's your PS crossed with your direction vector divided by the magnitude of your direction vector. And we know it's a cross product because line rhymes with sine and sine uses the cross product. On the other hand, if it's distance between a point and a plane, it's going to be PS dotted with n divided by the magnitude of n, where n is the normal vector. And again, PS is the usual vector from a point on the thing you have to the point you're trying to find the distance to. It's probably memorizable. I just never do. Also because I always have to derive it when I'm showing it to people, so it doesn't really make sense for me to memorize it anyway. Okay. I think these are kind of neat equations, but yeah, you probably do want to memorize them so that when you're actually doing these problems, you can just kind of toss it out there real quick. What else do we have on the docket here? Ooh, yeah, this is okay. So here's one that I think is interesting. This is going to combine some of the stuff. So there's really no other distance between things formula. Like it's either point in a line or point in a plane. That's kind of it. But what if someone asked you the following? Find the distance between these two lines. L1 given by, I'm just gonna write it as a position vector given by R of t equal to 1 plus 2t, negative 3 plus 4t, comma, negative 1 minus t. That's R1 of t, apologies. And then R2 of, let's use a different letter, S, is given by the position vector 4 minus 2s, 1 plus 3s, and 2s. And of course, you could write the parametric equations, x equal to 1 plus 2t, y equal to that, z equal to that, and then x equal to that, y equal to that. But easier this way. Okay. When is this question interesting? Well, I'll point out first, these lines aren't parallel to each other, right? If you look at the direction vectors they both have, the direction vector here is just the vector that's 2, 4, negative 1. And the direction vector here is the vector that is negative 2, 3. Oops, I wrote 2z here. I meant to write 2s. Sorry about that. That's a little confusing if you do it the wrong way there. The direction vector here would be negative 2, 3, 2. Clearly, these direction vectors are not multiples of each other, so the lines aren't parallel. Well, there's only 3 options for what lines can be in orientation to each other in space. They're either parallel, they intersect, which would mean the distance between them was 0. That's also not very interesting. Or they're skew, which these lines are skew. So that's kind of the most interesting version of the question is how do we find the distance between two skew lines? Well, let's draw a picture. If the lines are skew, like we talked about last time in class, it means they live in planes that are parallel to each other. So like you can imagine one of them going this way on the floor, and one of them going that way on the ceiling, or some other non-parallel directions. But they'll never touch each other because they live in parallel planes. Well, the fact that they live in parallel planes is actually the clue we need to help us figure out how to do this. So let's look at a picture that I can draw this picture. So here's one of my planes. Here's the other plane. So these skew lines live in parallel planes. So maybe one of them is going this way. There's L1. And one of them is going in a totally different kind of direction. There's L2. Yeah, question.
How do we know that they're parallel?
Well, so I told you the lines were skew. We didn't do the work to show that. but I was kind of talking through how the fact that the lines are definitely not parallel because the vectors that give you the line directions aren't multiples of each other. And it wouldn't be interesting to ask this question if the lines intersected each other. Because if the lines intersected each other, the distance would be zero. So, but you were definitely starting this problem being told that the lines were skewed. If we were just given lines and asked to find the distance between them, then you'd first have to go through the process of, well, are they parallel? Do they intersect? And if both of those aren't true, then you go to the fact that they're skew lines and do the rest of this process. So here's what's going to happen. There is some point between these two lines that is the closest point. And it's going to be maybe like, say, draw this in green here. It's like right there. And what's interesting here is that this line segment connecting these two lines has to be perpendicular to both of these lines. So imagine that we just, for a second, drew L1 down here like that. So we just moved L1 down. It's like the ghost of L1 or the shadow of L1 down there. Well, if you look at L2 and L1, this third line or vector in a minute that is perpendicular to both of them, we could find by taking the cross product of L2 and L1. Right? If you're looking for a vector that's perpendicular to two other vectors, you do that by finding the cross product of the original two vectors. It feels a little weird because like it feels like the vectors aren't in the same spot, but again, right, the vector that points this way points that way, and we're just moving the vector part down. I should have said that instead. We're just moving the vector part down. That makes a little more sense actually. So to find, let's call this vector that is perpendicular to both of these planes, the typical choice, n, for a normal vector. And we're going to say that to find n, we use the cross product of the directions of the lines. V1 and V2. Okay, so our n is going to equal V1 cross V2. It does not matter which order you cross. I mean, it does matter in that you get a negative of your answer if you cross them in the opposite direction, but either vector, either n pointing up or n pointing down, will be sufficient to help us finish this problem. So let's find the cross product of V1 and V2. Why don't you all find the cross product of V1 and V2? I'll write it out here, but you do the work. All right, I'm getting the vector 11, -2, 14. Now what do we do with that? Well, now we're in one of our previous situations. If we just think about it the right way, we're going to try and find the distance between one of these planes and a point on one of the other planes that's on the line that we're looking at. So let's find a point on this line here. Let's say, so on L1, I'm just going to set t equal to 0 and get 1, -3, -1. So let's say this point here, that's our S, that is the point 1, -3, -1. And similarly, we can find a point P on the plane down here by setting S equal to 0 and call it 4, 1, 0. And again, you can use any points really. I'm just picking the easiest candidate. So over here, we've got the point 4, 1, 0, and that's our point P. And now this is the same problem we already did. We're trying to find the distance between this point over here and this plane down here. Because if we find the distance between these two planes, meaning this point and this plane, it'll give us the distance between these two lines. Because that distance there, which I'm trying to show you is not looking very good, right? That distance that happens to be the distance between these two planes is also the distance between these two lines. So we're back in the thing we already did. So let's see if I can remember the formula without looking. So we know that the distance between a point S comma 1, -3, -1, and the plane below it containing the point P, which is the point 4, 1, 0. Let's see, it's not a line, so we don't use sine, so we have to use cosine, meaning it's the dot product formula. So it's going to be the distance is equal to the magnitude of PS dotted with the only other vector you've got, which is n, divided by the magnitude of n. Oh, what's the vector n? Oh, n's right there. So it's going to be, oh, sorry, I made one small mistake. It's not that bad, but it's a mistake. I shouldn't have written magnitude here. It's not the magnitude of a vector, it's the absolute value of a number. That should be an absolute value there. Not a crime, but it's good to be correct. So then PS is going to be the vector 4 minus, be careful, James. It's the S coordinates minus the P coordinates. It's 1 minus 4, comma, -3 minus 1, comma, -1 minus 0, dotted with our normal vector, which is the vector 11, -2, 14, absolute value of all that. And then we're dividing by this the magnitude of our normal vector, which is the square root of 11 squared plus -2 squared plus 14 squared. I'll point out, just I think it's worth mentioning, if you get to this place on an exam and you feel like you're fighting for your life time-wise, stop there. Simplifying this might be worth a point or two, but like there's other more high-value targets on your exam. If you have time at the end, come back and do the simplification, but you did all the work, right? You found the distance, you just didn't simplify it into a nicer looking number. I guess maybe you should calculate the dot. Okay. Maybe I should calculate the dot product here and write it as -33 plus 8 minus 14. Throw some absolute values around that. Maybe stop there. But then if you have time, go to the end and say, okay, I've got, let's see, -39. So 39 over the square root of 321. That can't be right. Yeah, that's right. Okay, cool. There's something else I want to say. No, I don't want to say that. I'll have to go look because invariably someone always asks the question, how do you find the distance between two parallel lines? And I was like, I don't remember how. I just have to go think about it. It's usually easier than I think it is. I just literally don't remember how to do it. So I'll remind myself to think about that for next class. But let's look at one more thing. One more thing. Yeah, one more thing. Yeah, cool. One more thing. Yeah. One more thing. maybe two more things, but they're really related. So one more thing we want to find is find the angle between these two planes. We have x plus 2y plus 3z equal to 6, and x minus 2y plus 4z equal to 8. And as long as the planes aren't parallel, they have to have intersected each other. Yeah. Kind of on a related note, while you're visualizing something like that, here's something else I want you to take a second to visualize. If you have a line in space, it has to go through at least one of the coordinate planes. Like if you drew a line in this room, it would have to go at least through that wall or the floor. Now you can have all three, right? You can have a line going through all three coordinate planes. Like if you maybe started it below the floor over there and then had it shoot up this way and go through that wall there and then keep extending that back that way and hit that other wall there. So certainly a line can go through all coordinate planes, but it certainly has to go through at least one. One's not very interesting though, because if it goes through only one, it's usually like something like z equal to 5. Z equal to 5? No, it's not. No, sorry, z equal to 5 and x equal to 2. Where like two of the things are constant and the other thing just like changes. So not very exciting, but that point will come back up later. How do you find the angle between two planes? Well, we draw them. Here's one of my planes in blue. Let's call this plane 2 and this plane 1. Let's say this is plane 2. And here's my other plane in green. Let's make sure I can draw this well. Sure, that looks fine. It continues on that way. And so we're trying to find this angle right here between these two planes. And so what we're going to do to find that angle is we're going to find both of the normal vectors of these planes, which are easy to find, and then take their find the angle between them. So here's the vector that's normal to plane 2. And if I can draw this all right here. Sure. I feel like I've done myself a terrible job here of I feel like interesting. Oh yeah, that's right. Ha 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 ha. So, that's interesting. So I'm noticing a problem in my drawing here. It's okay. It's okay because it's not wrong. But to me, and probably to you, it looks like the angle I've drawn here is obtuse, and the angle between these two vectors is acute. And that is not incorrect. I just identified the wrong angle. This is the angle between the two planes. Right? So between two planes, there's always going to be two angles between them, one of them acute, one of them obtuse, unless they're both 90 degrees. So we'll do this and then we'll talk about what the answer is. All right, so our first normal vector is just the vector 1, 2, 3. Our second normal vector is the vector 1, negative 2, 4. I know it's been a minute since we found the angle between two vectors, but I'll remind you, cosine of the angle is just equal to the dot product divided by the magnitudes of the vectors multiplied together. So in this case, the dot product of n1 and n2 is going to be 1 times 1 plus 2 times negative 2 plus 3 times 4 divided by the magnitude of n1, which is the square root of 1 plus 4 plus 9, and the magnitude of n2, which is the square root of 1 plus 4 plus 16. So here we're getting that cosine of the angle is equal to 9 divided by the square root of 14 times square root of 21. So I'll point out, based on the fact right now that cosine of this angle is positive, we know the angle we're going to find here is going to be the acute angle, right? Because cosine is positive in the first quadrant and negative in the second quadrant. So here, we find that theta, and let's label this one over here as theta 1 and this red one over here as theta 2. Theta 1 is equal to the arc cosine or the inverse cosine, whichever you prefer, of 9 over the square root of 14 times 21. And if you use a calculator, it's approximately, where'd you go there? 58.3 degrees. If you get asked questions like this on WebWork or whatever the other program is, make sure you pay attention to whether they want the answer in degrees, which is atypical, or radians, which is more typical. So in radians, this would be approximately 1.018 radians. And then the other angle would be the complement. So theta 2 would be approximately 180 degrees minus 58.3, which is 121.7 degrees, or whatever the equivalent would be in radians, which I did not write down. Question, yeah. Say that one more time. Oh, I literally just, for the second angle, I just subtracted 180 minus 58.3. I just didn't show my work. So for theta 2 is just 180 degrees minus theta 1. And we can save that other part for next time. Feels like a good day to end 3 minutes ago. All right, that's all I have for today. If there's something else I want to tell you guys. I don't know. Make sure you got your name on the attendance sheet, and we'll see you all on Wednesday. I remember how to stop things here. You're welcome. Oh, I forgot the control. I hid the controls. I'm like, why can't I stop this thing? So I hid the controls. There we go.